So first semester was calculus and slope. Everything was about slope. We found the slope of this, and it meant that was the derivative. And then we found the slope of the derivative, and that meant concavity was just slope, 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 slope. Second semester, which basically equates to second semester of like a college class, right? So this is exactly where college classes are coming back from Christmas vacation, and they're starting exactly at the same place that we are. The difference in a college class, second semester, is that where we stop right before spring break and then we prep for the AP exam, that college class would keep going. Okay, and that college class then is going to do the rest of the BC curriculum. So we get up through March and we stop with chapter 8. A college class is going to, like the BC class, is going to do 9, 10, and 11 as well, those last little bits. Okay? All right, so calculus and area. So what I want to talk with you first, if you've had a physics class, this will look a little bit familiar to you. We want to start with the graph of a velocity function. So velocity functions are graphed compared to time on your x-axis, and velocity being measured on your y-axis. All right, so let's say that time is measured in seconds, and then let's say our velocity is measured in meters per second. Okay, so some of you have taken a physics class and you have done a little bit of work with this, where you've looked at a velocity and maybe velocity is going like this, and then it goes up for a while, and then it goes down, and then it goes across, and then it ends. And then maybe you're asked, how far did the object travel? Okay, what was the distance traveled? And that would be the question, and you learn how to interpret that velocity graph. Okay, so the question is then distance traveled. Well, let me ask you, what units would distance be measured in? Not in this question, not kilometers, it would be measured in meters. Okay, and the way we would get that is if you take meters per second, which is the velocity unit, and you multiply it by seconds, which is the time unit. The time units cancel each other out, and you're left with meters. Okay, so it is the measurement of the y-axis multiplied by the measurement of the x-axis. That's like length times width, or base times height. And so that is essentially finding the area underneath this velocity graph. So the physics of that is this. The area under a velocity graph but above the time axis. Okay, it has to be above the axis in that first quadrant. So the area under a velocity graph, but can still above the time axis, is equal to the distance traveled. So how would you figure out the geometry of this shape right here? What would you do if I said find the geometry of that shape? How would you chunk that up or break that up? Okay, make a rectangle, sure. Okay, so say, all right, I can do, maybe find a rectangle first, so figure out that first rectangle that way, okay, because rectangles are easy. Okay, then what would you do? Oh, do another rectangle over here. Okay, another rectangle over here. Oh, okay, sorry, I misunderstood you. Okay. Okay, all right, what else?
I guess you could just make that all one big rectangle.
Like cross like this, okay. So you chunk it up into maybe another rectangle. Okay, then what?
But then there's that weird shape.
Okay, so that weird shape, right. Okay, so you want to maybe do, you were saying maybe like the top triangle up here. Okay. All right, and then you mentioned a weird shape. It is perfect. Okay, what is it perfectly a shape of? It is. It's a trapezoid. Yeah, this shape right here is a perfect trapezoid. It has 3 straight sides. And there's the geometry formula for a trapezoid too. So it would just take several different geometry formulas, a couple rectangles, triangle, and a trapezoid. But we have geometry formulas for all of those. If you didn't remember a trapezoid, you could look it up. But for sure, you could do a trapezoid as well. Okay, so that's how you would approach that, by chunking that into different geometry pieces. And all the mathematicians did that. Okay, that was how Newton did it, until Leibniz figured out how to do it the calculus way. And so that's where we're going to start chapter 6 with is there a calculus way to find the area under that curve instead of a geometry way? And the answer is for sure yes. Okay, so let's jump into how we would do that. All right, so let's suppose that your velocity function is the simple function 10 minus t over the interval 0 to 3. Find the distance. Okay, so think about it geometrically. 10 minus t is a straight linear line with a slope of -1 and a y-intercept of y-intercept of 10. So we've got 10 up here, and then we've got that geometry coming down that way, and we're only going 0 to 3, so time 3 is about that much. And so we want the area of that now trapezoidal shape. Now a trapezoid is just a rectangle and a triangle put together. Okay, so you could do a simple rectangle added to a simple triangle on top of that and come up with it. But it is helpful to know the area of the trapezoid. Okay, the area of a trapezoid is 1/2 base times the 2 heights put together on either side, height 1 plus height 2. And so in this case, the trapezoid has a base of 3, and the taller height is a height of 10. And what's the smaller height? How tall is that? Can you figure that out? It is. It's 7, okay, according to the line 10 minus 3. Okay, so 10 plus 7. So we're looking at 1/2 of 3 times 17. So 3 times 17 is 51. So 51 over 2. And so the distance traveled is 51 over 2 units. I didn't specify what the units were, but whatever the units are, that will be the units for that. So when the velocity graph is nice and linear, it works out great. All right, here's another velocity graph. So let's say the velocity graph is 10 minus t squared on the same interval, 0 to 3. Find the distance. Okay. So we're going to think about that geometrically again. 10 minus t squared. Okay, that looks a little different because this is now a parabola. We still have a y-intercept of 10, but it's going to curve this way as a parabola instead, hitting at the square root of 10, which is a little more than 3. So if I'm going from 0 to 3, 3 is right here. And so I've got not a trapezoid anymore, but I have a shape whose top is very much curved. Oop. All right, so I've got a different kind of shape. There is no geometry for that shape. So then what do? Well, we're going to do what Newton would have done. Okay, and so the approach was this. Okay, well, I don't have a geometry for that shape. It's not a nice trapezoid like it was before. Okay, so what I'm going to do is I'm going to split this into 3 pieces. I'm going to split it at 1 and 2, and then 3 is the end. All right, so one mathematician may have said, well, the heights keep changing, the heights keep getting smaller. So I'm going to use the smaller height, and I'm going to make a rectangle at the smaller height right there. How tall is that rectangle? We know that it started at 10, but how tall is it now? 10 minus what? 10 minus t squared, so what is it? Well, it's 9. Okay, so it's 10 minus 9. So that rectangle is 9. Okay, so how big is that first rectangle? Just the rectangle part of it, not the little curvy part at the top, but just the rectangle. How big is, how much area is there? Base times height, folks, come on. I know it's the first day back, but okay, we're looking at an area of 9. All right, so this one has an area, we'll remember, of 9. Okay, all right, next rectangle, it gets smaller again. How tall is that rectangle? Okay, well, it's coming up from the number 2, so 10 minus t squared, how tall would that be? I feel like you're not understanding how high that should be. Okay, that should be 6. Okay, and so what is the area of that rectangle? Just the second one. How wide is the base? No, the base is not 2. The base is only 1. It's from 1 to 2. All right, and the height of that is 6. Okay, so that is 6. All right, and my last rectangle, which is terribly not to scale, I apologize. Okay, how tall is that supposed to be? 1. It's supposed to be 1, because 10 minus t squared, that's 10 minus 3 squared. Okay, so that's a problem because I didn't draw that very well, but it's supposed to be 1 tall. And so how much area is in that single rectangle? Just 1. So the total is 9 plus 6 plus 1, which is 16 units. Is that accurate? Is it an under approximation or an over approximation? It's an under, okay, because I just did this area plus this area plus this area. All right, so 16 is an under approximation. Okay, well, let's try an over approximation. Let's make our rectangle that extra piece up there. And then let's make this rectangle the extra piece. And let's make that rectangle the extra piece. So they're going to be taller. Now, all right, how tall would the first rectangle be? 10. How tall would the second rectangle be? It's level with the other one, right? So how tall would that be? 9. And then the other rectangle would be 6. All right, so those would have an area of 10, 9, and 6. So those together, 10 plus 9 plus 6, that's 25 units. But all of those rectangles are too big because they all extend out beyond the curve. So that's too big also. So that's an over approximation. We had under approximation, we had an over approximation. So the real answer is somewhere between 16 and 25. That's not very accurate, is it? That's a pretty big window gap. Okay, so how can we make that more accurate still? Okay, so I'm going to start with a new drawing because mine's getting kind of messy, but it's the same. I'm going to draw the same thing. But maybe I'll try and make it a little bit more to scale. All right. And here's 3 and 1 and 2. Okay. There's 1, there's 2, there's 3. let's track the heights. We knew that we started at 10. This height is 9. This height is 6. That height's 1. It's a little better. It's not perfect, but it's a little better than what it was. Okay, so I've got 0, 1, 2, 3 across the bottom. I've got 10, 9, 6, and 1 as my heights. So how can we split the difference? How can we not have a rectangle that's too small? And how could we maybe not have a rectangle that was too big? Okay, well what we're going to do now is we're going to look at the midway points. So I'm going to zoom in on this so we can get that. What about at 0.5? What would the midpoints of each of these be? So at 0.5, at 1.5, and at 2.5. Again, we're using the curve 10 minus t squared. So you want your calculator out probably. Well, you can do that in your head. Can you do 10 minus 0.5 squared? You should know what 0.5 squared is. Okay, 0.5 squared is 0.25. So then what's 10 minus that? Okay, so this height is 9.75. Okay, what about the one next to it at 1.5? Okay, 1.5 squared, that's 2.25. Subtract 7.75. And then 2.5 is the x value. If you square that, that's 5, let's see, 25 is 5.25. And so subtract, we get 4.75. Okay, so draw rectangles through those points. So if I drew a rectangle at that height, if I drew a rectangle at the 7.75 height, and if I drew a rectangle at the 4.75 height. If that's where the rectangles are, what do you notice? Okay, now, what do you notice about the left side of the rectangle? Of all the left pieces? They're all underneath, right? And then what about the right pieces? They're all over. And so it's going to balance each other out. Okay, so you have you've got the gap to the left of 0.5, and then you have the gap from 0.5 to 1, but they're going to kind of balance each other out, at least better than before. And then the next space here, you've got space where you're missing pieces right here, but then you've got overage right here, and those will be pretty close to canceling each other out. And then the same thing is going to happen where you're under here, but you're over here. And again, those will hopefully cancel each other out. Okay, so now we have rectangular heights. The bases are all 1. So the first rectangle would be 9.75 for area if the base is all 1. And then 7.75 and 4.75. Okay, can you add those three numbers together? I'll let you use your calculators for that. 975, 775, 475. What do you get? Say it again. Maybe 21.75, but he's not sure. Okay. That is probably the best approximation we would have. We knew it had to be between 16 and 25, and 2175 was pretty close. How would you make that better? Any ideas? Andrew? Rectangles? Yeah, make more rectangles. How many rectangles am I working with here? 3. What would be double the number of rectangles? Make 6 rectangles, or make 12 rectangles, or make 24 rectangles. The more rectangles you have, the more accurate you will be because you have less gap. You'll have less error. Yeah, Jake, did you have a question? No? Okay. This is called the rectangular approximation method. All right, RAM. Rectangular approximation method. There are three methods we saw here. We saw LRAM. LRAM were the blue rectangle, LRAM were the green rectangles that I drew, where the left side determines the height. Okay, so the height is determined by the left side. Okay, then there's RRAM. There's where the height is determined on the right side, which is what I did in blue. And then finally, you have what's called MRAM, where the height is determined at the midpoint. Okay, here's where it gets fun on the calculator. All right, last one. All right, let's go with the function that's cubic this time. Let's do x cubed minus 1 on the interval from 0 to 4. So if you're going on the interval 0 to 4, how many rectangles do you think would be a logical good number to choose? 4. Yeah, you kind of go with what your interval length is and then make your rectangles accordingly. Okay, so I always like to visualize it. It really helps me to have a picture in my mind of what's going on. So a cubic is going to have a y-intercept of -1. Oops. And it's going to come up like this. Okay, there we go. The rest of the cubic is over here. I don't really need the rest of it, but that's where the rest of that is. And if we're going to divide this up into 4, oh boy, I really need to try drawing mine a little bit better. One more time. Ugh, whatever. Okay, there's 1. So there's 2, and there's 3, and there's 4 way off on the edge there. Okay, track your heights at all of your intervals. Okay, I'm way off the screen here, but okay, just using the function, track your heights. All right, we know that this height down here is -1. We know that this one is 0. Okay, 2 cubed minus 1, that height is 7. 3 cubed minus 1, that height is 26. 4 cubed minus 1, that height way up here is 63. Okay, those are all my heights. All of the bases of my rectangle are all going to be 1. So if I'm going to do my left height, the left side is going to determine the height of every rectangle. So if you're doing left, but you only have 4 intervals, how many height values are there right now? Count them. -1, 0, 7, 26, 63. How many height values are there? There are 5, but you're only doing 4 intervals because everything has 2 sides. So when you're doing on the left, when you start with the height of -1, because that's on the going from left to right, which one will you not use? You won't use the 63. And when you're doing the right sides, where the right side determines the height, which one won't you use? You won't use the -1. I'm just going to quick draw the right side. The right side would all be these. It'd be really tall, big rectangles. And then the last rectangle would be just a rectangle of 0. Those would be all the rights. 65, 26, 7, and 0. If I was doing the lefts would be, ooh, I'd have a -1, which means you're going to have a negative answer, and then 0, and then 7, and then 26. So that's going to be really small, because you're going to even have a negative rectangle that you have to do. So the best is going to be when you do your middle, and you will need your calculator to help you figure out what all the middles are, because there's going to be a middle here, and here, and here, and here. There's only 4 middles. Okay, there are 5 height values, and you always don't use 1, but there are 4 middle values, and you'll have to figure out the 4 middles. But always work it out so your interval length on the bottom is 1. It makes your math way easier if your interval length is 1.